Tonight, I want to tell you about the day we spoke to the universe. Not metaphorically, not in the poetic sense that science itself is a kind of conversation with the cosmos. I mean literally. On a specific afternoon, on a specific date, from a specific place on Earth, human beings aimed the largest radio telescope on the planet at a target 25,000 light-years away and pressed a button. For 169 seconds, we transmitted. What we sent was small, 1,679 binary digits, ones and zeros, a sequence that, arranged correctly, forms a picture containing everything we thought a distant civilization would need to understand who we are, where we live, and what we are made of. We sent our chemistry, we sent our mathematics, we sent the shape of the molecule that encodes all life on Earth. We sent a picture of a human being, we sent the address of our solar system, we sent it toward Messier 13, a cluster of approximately 300,000 stars packed tightly together, 25,000 light-years from Earth, a place so far away that the message will not arrive for another 24,948 years, and any reply, if one were ever sent, would not reach Earth for approximately 50,000 years. Nobody expected a reply, but the fact that we sent the message at all, the fact that we aimed our most powerful transmitter at the sky and announced ourselves to whatever might be listening, that fact terrified some of the most serious scientific minds on the planet. Not immediately. The terror came later, slowly, as physicists and astronomers and philosophers began to sit with the implications of what had been done, as they asked questions that had no comfortable answers, questions like, what if something is listening? What if something has the technology to receive our signal and the capability to respond? And what if that something is not friendly? What if announcing our existence to the universe was the most dangerous thing we have ever done? Tonight, we are going to sit with that question. We are going to go back to 1974, to the mountains of Puerto Rico, to the largest dish antenna on Earth, and watch the message leave. We are going to decode it, every pixel, every section, every piece of information we chose to share with the cosmos. We are going to follow the debate that followed, quiet at first, then urgent, then sharp, about whether humanity had been reckless, whether we had just handed our coordinates to predators we couldn't imagine, whether the silence of the universe was a warning we had ignored, and we are going to end somewhere unexpected, somewhere that sits at the boundary between science and something older, the ancient human need to call out into the dark and ask if anyone is there. This story starts with a man, and a question he spent his entire life trying to answer. Get comfortable. We have a long way to go. His name was Frank Drake, born in 1930 in Chicago, raised in a household where religion and science competed for his attention. By his own account, he was 8 years old when he first seriously considered the possibility that life might exist somewhere other than Earth, not as fantasy, not as science fiction, as a genuine scientific question. He studied astronomy at Cornell University, then earned his doctorate at Harvard, and in 1960, just a year after joining the staff of the National Radio Astronomy Observatory in Green Bank, West Virginia, he did something that had never been done before in any systematic way. He aimed a radio telescope at the sky and listened for signs of intelligent life. The project was called Project Ozma, named after the princess of the Land of Oz in L. Frank Baum's stories, a distant, exotic, difficult-to-reach place inhabited by strange beings. Drake chose 2 nearby sun-like stars as his targets, Tau Ceti and Epsilon Eridani, both within about 12 light-years of Earth. He observed each for approximately 150 hours at a frequency of 1,420 MHz, the frequency at which hydrogen naturally emits radio waves, a frequency Drake reasoned any technically advanced civilization would recognize as significant. He heard nothing meaningful, no signal, no pattern, just the static of the cosmos. But Project Ozma had done something important. It had turned the search for extraterrestrial intelligence from philosophical speculation into experimental science. Drake had demonstrated that you could actually look, that you could point instruments at the sky, at specific targets, at specific frequencies, and ask the question empirically, rather than just theoretically. The following year, in 1961, Drake convened the first serious scientific conference on the search for extraterrestrial intelligence. It was held at Green Bank, and it brought together a small, extraordinary group: astronomer Carl Sagan, chemist Melvin Calvin, physicist Philip Morrison, neurologist John Lilly, and a handful of others. They called themselves, informally, the Order of the Dolphin, a reference to John Lilly's work on dolphin intelligence, which had suggested that complex non-human communication might be more achievable than previously thought. At that conference, Drake presented what would become his most famous contribution to science. Not a discovery, not an observation, but an equation. The Drake equation. It was not, strictly speaking, an equation designed to produce a precise answer. It was a framework, a way of organizing the problem, of identifying what you would need to know in order to estimate the number of detectable civilizations in our galaxy at any given moment. The equation begins with the rate at which stars form in the Milky Way. It multiplies by the fraction of those stars that have planets. It multiplies by the fraction of those planets that could support life. It multiplies by the fraction of those planets where life actually develops. It multiplies by the fraction of those life-bearing planets where intelligence evolves. It multiplies by the fraction of those intelligent species that develop technology capable of producing detectable signals. And finally, it multiplies by the average length of time such a civilization survives in a detectable state. Most of the factors in the Drake equation in 1961 were unknown. They are still debated today, but the equation served its purpose. It forced the question into a quantitative form. It forced scientists to think about what they would need to know, and it revealed which factors mattered most. The last factor, how long a technological civilization survives, turned out to be the most important and most unsettling. If civilizations routinely last for millions of years, the galaxy might be full of them. If civilizations tend to destroy themselves or fade within a few thousand years, the galaxy might be empty, or nearly so. This last term, L, became in Drake's mind the most important question in the equation, and answering it, he felt, required humanity to demonstrate that at least one civilization could survive its own technology. Drake spent the rest of his career thinking about these questions, and by 1974, he was ready to take the next step. Not just listening, talking. We know and understand the Arecibo message. You first need to understand the instrument that sent it. The Arecibo Observatory sits in a natural limestone sinkhole in the mountains of northwestern Puerto Rico, near the town of Arecibo. The mountains there are karst terrain, ancient limestone riddled with sinkholes and depressions formed over millions of years by water dissolving the rock. The engineers who designed Arecibo, led by Cornell University astronomer William E. Gordon, found one of these natural depressions and decided to use it. They built a dish into it, not a dish that could move and point in different directions the way conventional radio telescopes work. A fixed dish, conforming to the shape of the sinkhole, built into the ground itself, 305 meters across, nearly 1,000 feet in diameter, spanning an area of approximately 73,000 square meters, roughly 8.5 football fields, side by side, end to end. The dish was made of approximately 38,778 perforated aluminium panels, each one individually adjustable so that the surface could be maintained to the precise parabolic curvature required for focusing radio waves. The panels did not touch. They were suspended on a mesh of cables above the ground, allowing the natural terrain to drain rainwater through. Above the dish, suspended on cables from 3 concrete towers rising around the rim of the sinkhole, was a massive platform, a 900-ton instrument platform, hanging 150 meters above the center of the dish. This platform held the receivers, transmitters, and equipment needed to focus, amplify, and process the radio signals reflected by the dish. The entire structure was extraordinary. There was nothing like it anywhere on Earth when it was completed in 1963, and nothing comparable was built until China completed the FAST telescope, the 500-meter aperture spherical telescope, in 2016. Arecibo could not point at a specific star and track it the way a steerable dish telescope can. The dish was fixed in the ground, but the instrument platform above it could move within a limited range, allowing the telescope to be directed at any point within about 20 degrees of the local zenith. And as Earth rotated, different parts of the sky drifted through the telescope's field of view. For Drake's purposes in 1974, Arecibo had one other critical capability. It could not only receive radio waves, it could transmit them. A powerful transmitter could be focused by the dish into an extraordinarily narrow, intense beam aimed precisely at a distant target. The effective radiated power of the Arecibo transmitter, when the dish focused its output into a beam, was approximately 20 trillion watts. 20 trillion watts. To put that in perspective, the total electrical generating capacity of the entire United States in 2024 is approximately 1 trillion watts. Arecibo's focused beam, in terms of signal intensity in the direction it pointed, was equivalent to 20 times America's entire electrical output, concentrated into a single radio beam. A civilization anywhere in the Milky Way with a radio receiver the size of a Arecibo could, in principle, detect that beam if it happened to be pointing in their direction. This was the instrument Frank Drake and Carl Sagan decided to use. Before we get to the message itself, we need to understand the world of 1974, because the Arecibo message did not emerge from nowhere. It emerged from a specific cultural and scientific moment, a moment defined by new discoveries, new ambitions, and a particular set of people who believed that the search for life beyond Earth was one of the most important scientific questions in history. Carl Sagan was 39 years old in 1974. He was already famous, or becoming famous. He had worked on the Mariner 9 mission to Mars. He had been involved in designing the Pioneer plaque, the golden message that had been attached to Pioneer 10 just 2 years earlier. He had published papers on the origin of life, on the atmospheres of Venus and Jupiter, on the possibility of intelligent life in the cosmos. Sagan was unusual among scientists of his generation. He was a genuine scientist, rigorous, mathematical, demanding of evidence, but he was also a communicator of extraordinary gifts. He could take the most abstract astronomical concepts and render them in language that non-specialists could feel as well as understand. And he believed, deeply and seriously, that the question of whether we are alone in the universe was not merely an academic question, but a question with profound implications for what it means to be human. In 1974, the space program was at a particular moment. Apollo had ended. The last moon landing, Apollo 17, had been in December 1972. The era of boots on the lunar surface was over, at least for the foreseeable future, but the robotic program was expanding. Pioneer 10 had flown past Jupiter the previous year. Viking, the Mars lander mission, was in development and would launch in 1975 to search for signs of life in the Martian soil. The question of life in the universe felt, in 1974, closer than it ever had before. It was in this context that Frank Drake, working with Sagan and a small group of colleagues, decided to mark a special occasion with a gesture. Arecibo had been upgraded. The observatory had completed a major renovation of its antenna surface, improving its sensitivity and its transmitting power significantly. On November 16, 1974, there would be a ceremony to celebrate the upgraded telescope, and Drake had an idea for how to mark the moment. He would send a message to the stars, not because he expected a reply, not because he seriously believed that whatever he sent would be received and decoded in his lifetime, or in his grandchildren's lifetime, or in his great-grandchildren's lifetime. The message would take 25,000 years to reach its target. Drake was not delusional about that. But the act of sending a message, the act of encoding a meaningful signal and transmitting it toward the cosmos, would demonstrate something. It would show that human beings had achieved a level of technological sophistication sufficient to communicate across interstellar distances. It would show that if other civilizations at similar levels of development were transmitting, we would be able to detect them. And it would force the scientists in the room to think very carefully about what you would put in such a message, what you could put in such a message, given that you share no common language, no common cultural reference, no common physical experience with the recipients. What is universal? What can you say to a civilization that might be completely unlike us, using only mathematics and physics? Drake, Sagan, and their colleagues sat down to answer that question. Designing a message for an unknown civilization is harder than it sounds. You cannot assume they speak English. You cannot assume they have any language at all, in the human sense. You cannot assume they have visual systems analogous to human eyes, or auditory systems analogous to human ears. You cannot assume they experience time the way we do, or that they organize information the way we do, or that they have any of the cultural frameworks through which humans make sense of the world. What you can assume, and this is the critical assumption, is that they understand mathematics, that they understand physics, that if they have achieved a technology capable of interstellar communication, they have independently derived the same basic mathematical truths that human beings have derived. The prime numbers are the same everywhere. The properties of the hydrogen atom are the same everywhere. The laws of physics are universal. This is the foundation on which all serious attempts at interstellar communication are built. Mathematics is the only language that might be truly universal, the only framework of meaning that does not depend on the specific evolutionary history, sensory apparatus, or cultural development of a particular species. Drake's first design choice followed directly from this. The message would be encoded in binary, ones and zeros, not because binary is especially elegant, but because binary is irreducibly simple. There are only two states, on or off, 1 or 0. In a radio transmission, this maps directly to the presence or absence of a signal. Any civilization capable of receiving a radio transmission should be able to identify binary encoding. The message would be 1679 bits long. This specific number was chosen with great care. 1679 is the product of two prime numbers, 23 and 73. 23 multiplied by 73 equals exactly 1679. And crucially, those are the only two ways to factor 1679 into two whole numbers. 1 tac 1679, or 23 tac 73. Since 1679 itself is not prime, any civilization receiving a sequence of 1679 binary digits and attempting to arrange them in a meaningful grid would quickly discover that only a 23 by 73 arrangement, or a 73 by 23 arrangement, produces anything coherent. The choice of prime numbers was deliberate. Prime numbers have a property that no accident can easily replicate. They cannot be produced by multiplying two smaller whole numbers together. A sequence of 1679 digits arranged randomly would not have this property. If you received a sequence of exactly 1679 digits and found that arranging it in a 23 by 73 grid produced a coherent picture, you would immediately recognize that the number 1679 had been chosen intentionally and that the 23 by 73 arrangement was the intended one. Mathematics leading you to the message itself only visible when you know how to unfold it. This is the elegance of the Arecibo message, not just what it says, how it is designed to be decoded. The message teaches you, through its own structure, how to read it. Drake and Sagan drafted the content. They argued about what to include and what to leave out. Every bit of information had to earn its place. The message was 1679 bits total, which when arranged in the grid gives 23 columns and 73 rows. That is 1679 pixels, each one either black or white. In that space, you have to convey everything you want an alien civilization to know about the beings who sent the message. What would you put in 1679 pixels? The Arecibo message, arranged in its 23 by 73 grid, divides into 7 distinct sections. Each section communicates a different category of information. Together, they form a complete compressed portrait of intelligent life on Earth in 1974. Let's walk through each one. The first section, numbers. At the very top of the message, the first 4 rows of the 73-row grid are the numbers 1 through 10, written in binary. Binary notation uses powers of 2. 1 is 1, 2 is 10, 3 is 11, 4 is 100, 5 is 101, and so on. The numbers 1 through 10, in binary, are written from right to left, an unconventional direction that was included deliberately to teach the reader which way to read the rest of the message. Why start with numbers? Because counting is the most fundamental operation in mathematics. If the recipients can decode this section, if they recognize that this sequence of ones and zeros represents the integers from 1 to 10, they now know the numerical system used in the rest of the message. They know what binary means in this context. They have the key. It is the same logic as the Rosetta Stone. Give the reader something they already know, encoded in the system you're using, and they can use that knowledge to decode everything that follows. Immediately below the number sequence are 5 columns of dots, each column representing a specific atomic number. Reading the columns, the numbers are 1, 6, 7, 8, and 15. These are not arbitrary numbers. They are the atomic numbers of hydrogen, carbon, nitrogen, oxygen, and phosphorus, the 5 elements that make up the nucleotides of DNA, the molecule that encodes all genetic information in all known life on Earth. Hydrogen, atomic number 1, carbon, 6, nitrogen, 7, oxygen, 8, phosphorus, 15. The message is saying, here are the elements that we are made of, the building blocks of our chemistry, the atoms from which we, and all life on our planet, are constructed. Any civilization with knowledge of atomic physics, any civilization that has discovered the periodic table, which is a discovery that follows necessarily from the laws of quantum mechanics, and is therefore universal, would immediately recognize these 5 numbers as the atomic numbers of 5 specific elements. And any civilization with knowledge of biochemistry would recognize that these 5 elements together form the core of DNA. We are telling you what we are made of. The third section, the nucleotides. This is the most complex and most information-dense part of the message. It spans the next several rows of the grid and encodes the chemical formulas for the 4 nucleotide bases of DNA: adenine, thymine, guanine, and cytosine. usually written as A, T, G, and C. Each nucleotide is represented by the numbers indicating how many atoms of each of the 5 elements it contains. Adenine, for example, contains 5 carbon atoms, 5 hydrogen atoms, 5 nitrogen atoms, 0 oxygen atoms, and 0 phosphorus atoms. This information is encoded in binary form, with the 5 atomic numbers provided in section 2 serving as the key. This section of the message is the most biochemically specific. It is not just saying that life on Earth uses these 5 elements. It is saying that life on Earth stores its genetic information in a molecule made of 4 specific chemical units, whose compositions can be precisely described. It is providing the molecular vocabulary of terrestrial biochemistry. If the recipients of the message understand molecular chemistry at the level required to build a radio telescope, and by definition, any civilization that can receive the message must, they would be able to look at these formulas and recognize them. Or, if they had never encountered these specific molecules, they could at least understand that we were describing a specific biochemistry, and begin to understand what kind of chemistry produces creatures capable of sending radio signals. Below the nucleotide formulas is a number. The number is large, approximately 4.29 billion. This number, encoded in binary, is the approximate number of nucleotide base pairs in human DNA. In 1974, the precise sequencing of the human genome was decades in the future. The Human Genome Project would not begin until 1990 and would not be substantially completed until 2003. But the approximate size of the human genome, approximately 3 billion to 4.5 billion base pairs, depending on how you count, was known from earlier biological work. The message is saying our genetic information is encoded in a molecule approximately 4.29 billion units long. Flanking this number, on either side of the grid, are 2 twisted strands, a visual representation of the double helix structure of DNA. This is the only truly pictographic element in the first half of the message. The double helix is immediately recognizable to any biologist as the structure of DNA, the famous discovery made by Watson and Crick in 1953, building on Rosalind Franklin's X-ray crystallography data. But here is the hope embedded in this section, that even a civilization that has never encountered DNA might look at these 2 twisted parallel strands connecting the nucleotide structure to the numerical information and understand that this represents a double-stranded information molecule, that the structure itself carries information about how genetic information is organized, a message within the message, the shape of the molecule telling you something about how the molecule works. This is the most visually immediate part of the message, the part that is most immediately legible as a picture rather than a sequence of numbers. In the center of the grid, between 2 blocks of information, is a simplified outline of a human being, a stick figure of sorts, recognizable as bipedal, bilaterally symmetric, with a head, a torso, 2 arms, 2 legs, not detailed, not realistic, just the essential shape. Here is what the beings who sent this message look like. To the left of the figure is a number, encoded in binary, 14. To the right is another number, 4,292,853,750. The number 14 represents the height of a human being in units of the wavelength of the transmitted message. The Arecibo message was transmitted at a wavelength of approximately 12.6 centimeters. 14 times 12.6 centimeters equals approximately 176 centimeters, about 5 feet 9 inches, which is reasonably close to the average adult human height. This is how the message encodes physical scale without using any Earth-specific units. We are not saying 1.76 meters tall. The meter is a human unit with no universal meaning. We are saying 14 times the wavelength of this transmission tool, which gives any recipient, who by definition knows the transmission frequency, the exact physical scale of the figure. The number 4,292,853,750 represents the human population of Earth at the time of the transmission, approximately 4.3 billion people. We are telling you there are roughly 4 billion of us. This section of the message is perhaps the most poignant. Somewhere in the stars, a sequence of 1,679 binary digits contains a tiny picture of a human being, simplified, pixel by pixel, a little crude, but unmistakably upright, unmistakably the shape of the species that pressed the button and let the signal go. Below the human figure is a diagram of the solar system, 9 circles in a row, 1 for the Sun and 1 for each of the 9 planets then recognized. This was before Pluto's reclassification as a dwarf planet in 2006. The third planet from the Sun, Earth, is shown raised slightly above the plane of the others, connected by a line to the bottom of the human figure. This is the address. This is how you find us. If you receive this message and you decode it and you reach this section, you know, the beings who sent this have 9 planets in their solar system and they live on the 3rd one from their star. Start from that. Use the pulsar map. But wait, there is no pulsar map in the Arecibo message. That was the Pioneer plaque. A different message, a different context. The Arecibo message locates us relative to our own star, but gives no information about where our star is in the galaxy. This was a deliberate choice, or perhaps not deliberate, perhaps an oversight. We will return to this later. At the very bottom of the message is a schematic representation of the Arecibo dish itself, a horizontal flat line representing the dish reflector, with a vertical line rising from the center, the suspended platform above. Below the dish, the number 2430 encoded in binary. 2430 represents the diameter of the Arecibo telescope in units of the transmitted wavelength. 2430 times 12.6 centimeters equals approximately 306 meters, close to the 305-meter actual diameter of the dish. This section serves 2 purposes. First, it tells the recipients how large the instrument is that sent the message, which tells them something about the technological level of the sending civilization. Second, and more subtly, it provides a scale reference. Any civilization attempting to understand the human figure in Section 5 can cross-reference it against the known size of the telescope in Section 7, building an internally consistent scale for the entire message. The message ends with the instrument that created it. We are saying, this is how we made this signal. This is the machine. This is the technology. November 16th, 1974. A Friday, Puerto Rico. The Arecibo Observatory. The mountains are green, the air is warm, the sky is clear. Inside the observatory, there is a ceremony happening. The upgraded Arecibo telescope is being formally dedicated, and the dedication includes a gathering of scientists, astronomers, and dignitaries who have come to mark the occasion. Frank Drake is there, Carl Sagan is there, a number of other prominent astronomers are present. The atmosphere is celebratory, Arecibo newly upgraded, more powerful than it had ever been, ready for another generation of science. At a specific moment in the afternoon, Drake gives the signal. The transmitter at Arecibo is activated. At a frequency of 2,380 MHz, the telescope begins to send. For 169 seconds, 2 minutes and 49 seconds, the dish radiates the Arecibo message. The binary digits stream out, each bit corresponding to a specific frequency shift in the transmitted signal. The message leaves the dish at the speed of light, focused into a beam of extraordinary precision, narrower than any weapon, aimed at the sky, aimed at Messier 13. Messier 13 is a globular star cluster in the constellation Hercules. It was catalogued by the French astronomer Charles Messier in 1781, though it had been observed earlier by Edmund Halley in 1714. It contains approximately 300,000 stars, packed into a sphere roughly 145 light-years across, located approximately 25,000 light-years from Earth. Drake chose M13 for practical reasons. It was in the observable sky from Arecibo at the time of the transmission. It was a large target. A cluster of 300,000 stars, rather than a single star, meant that the message would pass through many potential solar systems rather than just one, and its distance, 25,000 light-years, made it romantically impractical without being ridiculously distant. The message would arrive there. It would just take a very, very long time. The transmission lasted 169 seconds, and then it was over. The signal left Earth at the speed of light, 300,000 kilometers per second. It crossed the Moon's orbit in a little over a second. It crossed the distance to Mars, on the far side of its orbit, in just over 20 minutes. It crossed the distance to Jupiter in about 43 minutes. It reached the heliopause, the edge of the solar system, in approximately 14 hours. By the time the ceremony at Arecibo ended, and the guests had gone home, the Arecibo message had already left the solar system. It is currently somewhere between Earth and Messier 13, approximately 51 light-years from Earth, still traveling at the speed of light, still in the form of a coherent radio signal, though spreading slightly as it goes, losing intensity with distance following the inverse square law. It will arrive at M13 in approximately 24,948 years. When news of the Arecibo message became public, the initial reaction was largely positive. Newspapers ran the story. The transmission was described as a landmark achievement, a demonstration of human technological capability, a poetic gesture toward the cosmos. Carl Sagan, who was extraordinarily good at communicating the significance of these things to general audiences, explained the message clearly and compellingly. The public was charmed. Among scientists, the initial reaction was mixed but mostly warm. The message was widely recognized as a clever piece of design. The use of prime numbers, the layered encoding, the self-referential inclusion of the telescope at the end. Drake and Sagan received praise for the elegance of the design, but there was a group of people who were not charmed, a group who read the news and felt something other than wonder. They felt something closer to alarm. This group was small at first. Their concerns were not immediately taken seriously. In 1974, in the warm aftermath of Apollo, in the era of Carl Sagan and the golden age of optimism about space exploration, warning that we might have done something dangerous by sending a message to the stars seemed like the kind of worry that belonged in science fiction, not in serious scientific discourse. But the concerns were serious, and over the following decades, as physicists and astronomers and philosophers engaged more deeply with the implications of interstellar communication, those concerns grew, not smaller, but larger, more urgent, more refined, more difficult to dismiss. The controversy that began quietly in 1974 would eventually involve Stephen Hawking, Nobel laureates, internationally organized scientific commissions, and a debate that is still ongoing today, more than 50 years later. The first formal institutional pushback came from an unexpected direction: the Royal Astronomical Society of Great Britain. Shortly after the Arecibo message became public, the Royal Astronomical Society sent a formal letter expressing their concern, not to Drake or Sagan specifically, to the International Astronomical Union, the body that governs international collaboration in astronomy. The letter was careful and measured. It did not accuse anyone of recklessness. It did not invoke science fiction scenarios of alien invasion. It made a specific, narrow point that was, in retrospect, extremely well reasoned. The point was this: we had transmitted a message without any prior international consultation or agreement. We had made a unilateral decision on behalf of the entire human species to announce our existence to potential extraterrestrial civilizations. We had not asked whether this was wise. We had not asked whether there were potential risks. We had simply done it. The Royal Astronomical Society was not saying the Arecibo message was necessarily dangerous. They were saying that decisions of this magnitude, decisions that could potentially affect every human being on Earth, possibly for generations, should not be made unilaterally by a single research group without broader consultation. This was a governance argument, a procedural argument, and it was, in retrospect, a sound one. Frank Drake's response was somewhat dismissive. The message was a one-time ceremonial transmission, he pointed out. It was aimed at a target 25,000 light-years away, too far for any reply for 50,000 years. It was not a systematic, ongoing broadcasting program. The odds of any negative consequence were vanishingly small. He was probably right about the specific transmission, but the broader principle the Royal Astronomical Society had raised, should humanity have a policy about messaging extraterrestrial intelligence, was not so easily dismissed. And as the years passed, that question became more pressing. To understand why the Arecibo message became frightening to some scientists, you need to understand the Fermi paradox, because it is the Fermi paradox that gives the concern its teeth. The story goes like this. In the summer of 1950, the physicist Enrico Fermi was having lunch with colleagues at Los Alamos. They had been discussing a recent cartoon about aliens. The conversation turned, as conversations among physicists sometimes do, toward a mathematical observation. Fermi asked a question. It may have been rhetorical, it may have been entirely serious. The accounts differ, but the question was, where is everybody? Here is the logic behind the question. The Milky Way galaxy contains approximately 200 to 400 billion stars. Many of those stars, current estimates suggest the majority, have planetary systems. Many of those planetary systems should include planets in the habitable zone, the range of distances from a star where liquid water could exist on a planet's surface. By any reasonable estimate of the Drake equation, the galaxy should have produced intelligent, technologically capable civilizations many times over, across billions of years of available time. A civilization with sufficient technology, not science fiction technology, just a modest extrapolation of current human technology over a few thousand or million years, could spread through the galaxy, not necessarily at speeds near the light barrier, but at speeds that, sustained over millions of years, would allow a civilization to colonize or at least visit every star system in the Milky Way. The galaxy is approximately 100,000 light-years across, at 1% of the speed of light, a speed well within the reach of plausible future technology. Crossing the galaxy takes approximately 10 million years. 10 million years is not a long time on galactic scales. The Sun itself is about 4.6 billion years old. There have been billions of years available for any civilization that arose early enough to have spread everywhere. And yet, we see nothing, we hear nothing, we find no evidence, none at all, of any other technological civilization anywhere in the galaxy. No signals, no structures, no artifacts, no sign that any other intelligence has ever passed through our cosmic neighborhood. Where is everybody? This is the Fermi paradox, and it has no comfortable answer. There are many proposed solutions. We will explore the most important ones shortly. But the critical point for the Arecibo message is this. If the Fermi paradox has certain kinds of solutions, specifically, if the absence of alien civilizations in our observations is explained by the fact that something tends to silence or destroy them, then the implications for METI, for messaging extraterrestrial intelligence, are deeply troubling. What if they're not there because they announced themselves and something found them? The concept of the Great Filter was formalized by economist Robin Hanson in 1998, but the underlying idea had been discussed in various forms since Fermi's lunchtime question. The logic is straightforward. If the Fermi paradox is real, if the galaxy truly contains no other technological civilizations, or none that have made themselves known, then somewhere along the path from simple chemistry to galaxy-spanning civilization, there must be a step that almost never gets traversed. A filter, a barrier so high that virtually no species gets past it. The Great Filter might be in our past. Perhaps the development of complex eukaryotic cells, cells with nuclei, from which all complex life derives, was extraordinarily difficult and rare. Perhaps multicellular life was an unlikely accident. Perhaps the development of intelligence was a 1 in a trillion event. Perhaps the evolution of language, or culture, or technological civilization was the rare step. If the filter is in our past, if we have already passed through it, then our existence is evidence that we were among the vanishingly rare successes. In this scenario, the galaxy is empty not because civilizations get destroyed, but because they never arise. We are, or nearly are, alone. This version of the Great Filter is unsettling in its own way. The loneliness is absolute, but it is not frightening in the way that the alternative is frightening, because the alternative is that the Great Filter is ahead of us. What if civilizations do arise regularly across the galaxy? What if many species develop intelligence, language, technology, and the capacity for interstellar communication? And what if, at some point after reaching this level of development, they encounter something that destroys them? The something could be themselves, nuclear weapons, engineered pathogens, climate collapse. The list of ways a technological civilization might destroy itself is not short, and our own civilization's history provides some relevant data points. This is one version of the ahead filter. Civilizations regularly destroy themselves before they can become interstellar. But there is another version, darker, more specific to the METI debate. What if the filter is not self-destruction? What if there are civilizations, older civilizations, vastly more powerful than us, that systematically eliminate any new civilization that announces itself? No voice in the METI debate carried more weight than that of Stephen Hawking. Hawking was not a specialist in astrobiology or SETI, but he was the most famous physicist in the world, and when he spoke publicly on scientific matters, the world listened, and Hawking was deeply concerned about METI. He said so clearly, on multiple occasions, in language that left no room for ambiguity. His most quoted statement on the subject came in 2010, in a documentary series called Into the Universe with Stephen Hawking. He said, "If aliens visit us, the outcome would be much as when Columbus landed in America, which didn't turn out well for the Native Americans." He elaborated on this point in various ways over the years. Advanced civilizations, he argued, are likely to be advanced not just in technology, but in resources. A civilization capable of interstellar travel, of responding to the Arecibo message or any other intentional transmission, has, almost by definition, already mastered the challenge of sustaining itself within its own solar system. Such a civilization might be millions of years older than ours, and it might be facing resource constraints that make the colonization of other solar systems, including ours, an attractive option. Hawking's argument was not that alien civilizations would be malevolent in the way that movie monsters are malevolent. He was making a much cooler, more mathematical point. Malevolence is not required for danger. The native populations of the Americas were not destroyed by the European colonizers out of pure hatred, though hatred existed. They were destroyed as a side effect of contact between two civilizations at vastly different technological levels, in a context where one civilization needed resources the other occupied. The destruction was a consequence of the contact, not a goal of it. If an alien civilization found us and wanted what we have, our sun's energy, our planet's materials, our biosphere's chemistry, our technological disadvantage might be so vast that our preferences about the outcome would simply be irrelevant. Hawking did not say this was certain. He said it was possible, and he argued that the potential downside of being found by the wrong civilization was so catastrophic, not just for individuals or nations, but for our species as a whole, potentially for all life on Earth, that the prudent policy was caution, not transmitting our location, not waving our arms in the dark and announcing our presence to whatever might be listening. The Arecibo message, from this perspective, was not a poetic gesture, it was a security risk. In 2008, the Chinese science fiction writer Liu Cixin published a novel called The Dark Forest, the second book in his three-body problem trilogy. It became, over the following decade, one of the most widely read science fiction novels in the world, and one of the most intellectually serious explorations of the Fermi paradox in any form, fiction or non-fiction. The dark forest theory, as Liu articulated it, offers a specific solution to the Fermi paradox. It goes like this. Suppose there are many civilizations in the galaxy. Each one, like all life, is fundamentally oriented towards survival. Each one needs resources, energy, matter, space. The universe contains finite resources, and each civilization cannot know the intentions of other civilizations. It cannot trust them, because any sufficiently advanced civilization could build weapons capable of destroying a less advanced one, and there is no way to verify that a civilization's claim to peaceful intentions is genuine. In this situation, the rational strategy for any civilization is, stay hidden, do not broadcast your existence, do not announce your location, do not respond to signals from other civilizations, because responding reveals your position, and you cannot know whether the sender is a threat. And if you detect another civilization, if you discover that someone else has announced themselves, the rational strategy may be to eliminate them before they can become a threat, not out of malevolence, but out of self-preservation. A civilization that discovers another civilization knows only that the other civilization exists and has the technology to transmit. It does not know their intentions, their capabilities, or their trajectory. Eliminating them may be the safest option. The universe, in Liu's vision, is a dark forest. Every civilization is a hunter, moving silently through the trees. Anything that makes noise gets shot. The Arecibo message made noise. Liu Cixin is a novelist, not a scientist, and the dark forest theory is science fiction, not established fact. But the underlying logic, that in a universe with finite resources and imperfect information, the optimal strategy for a rational agent may be preemptive elimination of potential threats, is a version of game theory that serious researchers have engaged with. David Brin, the American science fiction writer and astrophysicist, has been perhaps the most persistent and rigorous scientific critic of METI. His argument is not precisely the dark forest theory. He doesn't necessarily endorse the specific mechanism Liu describes, but he makes a related point that is difficult to dismiss. We have been listening to the cosmos, running SETI programs, searching for signals from other civilizations for more than 60 years. We have heard nothing. The silence is almost total. The absence of detectable signals is a data point. It says something. What does it say? It might say there are no other civilizations, but it might also say that other civilizations do not transmit, that they have made the same calculation we are now making, that transmitting is dangerous, and that they choose silence. The universe might be full of civilizations, all of them quiet, all of them listening, none of them willing to be the first to speak, and we just spoke. The scientists who defend METI, who argue that messages like the Arecibo transmission are acceptable, or even desirable, have a set of counter-arguments that are also serious and deserve to be heard. The first is a practical point. It is too late to be silent. Humanity has been broadcasting radio and television signals since the early 20th century. These signals have been leaking into space continuously for more than 100 years. The sphere of space contaminated by human radio emissions has a radius of approximately 100 to 120 light-years. Any civilization within that sphere that had radio receivers sensitive enough to detect our signals has, in principle, already detected us. They know we are here. The Arecibo message did not reveal our existence to anyone within 120 light-years. Our existence was already announced by a century of radio and television and radar emissions. The cat, in other words, is already out of the bag for anyone in our immediate neighborhood. The second counterargument is philosophical. The scenario of predatory advanced civilizations quietly hunting for signals from younger species and eliminating them as soon as they announce themselves requires a specific set of assumptions about the psychology of advanced civilizations that may simply be wrong. We are reasoning from a sample size of one. The only technological civilization we know is ours, and our civilization, for all its violence and self-destruction, has shown a persistent trend toward greater cooperation, greater empathy, greater extension of moral concern over time. Species that have achieved the technological level required for interstellar communication may well have, in the process of achieving that level, developed cooperative instincts that make predatory behavior unlikely. Furthermore, a civilization capable of crossing interstellar distances or of sending weapons capable of eliminating threats across light years is a civilization with access to energy and resources on an astronomical scale. Such a civilization likely has access to stellar-scale energy sources. What would they need from us? Why would they bother? The third counterargument is evolutionary. If the dark forest logic were correct, if any civilization that announces itself gets immediately destroyed, we would expect the galaxy to fall silent very quickly in evolutionary terms. All civilizations would learn the lesson. All civilizations would stay quiet. There would be no signals to detect, because all civilizations capable of transmitting would quickly learn not to. But if that were the case, how would any civilization ever make contact? How would any civilization ever achieve the interstellar community that the optimistic vision of SETI imagines? The silence would be universal and permanent. And if the silence is universal and permanent, then the Fermi paradox is resolved by saying, they are all there, all listening, all afraid to speak, which is a deeply melancholy resolution, and one that, if true, we have only slightly worsened by adding our own voice. The fourth counterargument is specific to the Arecibo message itself. The message was sent to Messier 13. Messier 13 is 25,000 light-years away. Any civilization there that receives our message will be receiving it 25,000 years from now. If they respond immediately, at the speed of light, the reply would arrive at Earth in approximately 50,000 years. Whatever threat or benefit might arise from the Arecibo message is, at minimum, 50,000 years in the future. Our civilization, as currently constituted, is unlikely to exist in 50,000 years in any form that would recognize the continuity. In this view, the Arecibo message is philosophically interesting, but practically irrelevant. It is a message in a bottle thrown into an ocean that takes 50,000 years to cross. The Arecibo message was not the last time humanity intentionally transmitted signals toward potential extraterrestrial civilizations. In 1999, a group of researchers transmitted a message called Cosmic Call 1 from the Evapatria planetary radar in Ukraine. The message was more complex than Arecibo, including a more sophisticated encoding system and a broader range of information. It was aimed at 4 different target stars. A second cosmic call followed in 2003. In 2001, a crop circle appeared in a field in England near the Chilbolton radio telescope in Hampshire. The crop circle was in the form of a grid, and when decoded as a binary image, it appeared to be a response to the Arecibo message, modified slightly. The DNA section changed. The solar system section modified to show a third planet in a different orbit. The human figure replaced with something that appeared slightly different. Nobody has ever definitively explained the Chilbolton crop circle. The obvious explanation is that it was made by humans, either as an elaborate prank or as an artistic statement. But the precision of its encoding, the specific modifications to the Arecibo message, and the care with which it was constructed attracted serious analysis from several researchers. The most commonly accepted explanation remains human origin. But the episode illustrated something important. The cultural resonance of the Arecibo message had become deep enough that people were willing to invest extraordinary effort in creating a fake reply. In 2008, NASA transmitted the Beatles song Across the Universe toward the North Star, Polaris, which is approximately 430 light-years away. The transmission was made to mark the 40th anniversary of the song's recording and the 50th anniversary of NASA's founding. It was not intended as a serious scientific communication. In 2017 and 2018, a project called METI International transmitted a series of messages toward a nearby star system, GJ 273, also known as Luyten star, approximately 12.4 light-years from Earth. These messages were more sophisticated than Arecibo. They used a mathematical tutorial that built from simple counting toward more complex operations, and they were specifically designed around what the designers believed would be a more pedagogically effective approach to first contact. The METI international transmissions were controversial. A letter signed by approximately 26 researchers and scientists, including Stephen Hawking, David Brin, and several other prominent figures, had previously called for an international discussion before any further intentional transmissions were made. The letter explicitly warned against transmissions like those METI International ultimately made. The transmissions were made anyway. The controversy these transmissions generated reignited the broader debate, and the debate had by this point attracted the attention of not just astronomers, but anthropologists, ethicists, government officials, and philosophers who recognized that the question of whether to transmit messages to other civilizations was not merely a scientific question. It was a governance question, a question about who has the right to speak on behalf of humanity, and it remains, to this day, unresolved. The story of the Arecibo message has an unexpected coda, and it is worth telling. For more than 50 years after the 1974 transmission, the Arecibo Observatory continued operating. It discovered new classes of pulsars. It contributed to the first confirmation of gravitational waves, not through direct detection, but through observations of binary pulsars that were predicted by general relativity to be radiating energy as gravitational waves, causing their orbits to decay at a measurable rate. It tracked near-Earth asteroids and contributed to planetary defense efforts. It performed radar mapping of Venus, Mercury, and the surfaces of various moons. It contributed to SETI through its massive collecting area. For decades, Arecibo was irreplaceable. There was simply no other single instrument on Earth that combined its sensitivity and its radar power. China's FAST telescope, completed in 2016, surpassed Arecibo in collecting area, but Arecibo remained the only comparable radar transmitter. Then, in August 2020, one of the cables supporting the instrument platform broke. A subsequent inspection found that other cables had also suffered damage. Engineers began planning repairs, but on November 6, 2020, a second cable failed. The National Science Foundation, which operated Arecibo, assessed the situation and concluded that the structure could not be safely repaired. The decision was made to decommission and dismantle the telescope. Before the planned dismantling could begin, on December 1, 2020, the instrument platform collapsed. 3 of the support cables failed simultaneously. The 900-ton platform fell 150 meters into the dish, destroying the dish surface and creating a crater in the center of the bowl. The Arecibo Observatory, which had operated for 57 years, was gone in seconds. The collapse was captured on video. It spread across the internet quickly. Scientists and engineers who had worked at Arecibo for decades watched the footage and described feeling something they had not expected to feel about the destruction of a scientific instrument: grief. Carl Sagan had died in 1996. Frank Drake lived to see the collapse, then died on September 10, 2022, at the age of 92. He had spent his entire career listening for signals from the cosmos and sending a few back. He heard no replies in his lifetime, but the message is still out there. 66 years since Project Ozma, more than 50 years since the Arecibo message, decades of systematic searches, SETI programs scanning billions of frequencies, millions of stars, with equipment incomparably more sensitive than anything available to Frank Drake in 1960. And nothing. Not nothing in the sense of missing a few signals. Nothing in the sense of a comprehensive, sustained, technologically serious search yielding no confirmed detection of any signal of extraterrestrial intelligent origin. The WOW signal is the most tantalizing exception. Detected by astronomer Jerry Amon on August 15, 1977, using the Big Ear radio telescope at Ohio State University, a narrow-band radio signal at the frequency of hydrogen emission with an intensity approximately 30 times higher than the background. It lasted approximately 72 seconds, the maximum time that a source in the fixed sky could appear in the telescope's beam as Earth rotated. Amon circled the printout and wrote "WOW" in the margin, giving the signal its name. The WOW signal has never been detected again. It has been searched for many times, with more sensitive equipment, in the same region of the sky. Nothing comparable has been found. Its origin remains unexplained. It may have been a terrestrial radio frequency interference event. It may have been a satellite or spacecraft transmission. It may have been something else. It has never been confirmed as extraterrestrial. and it has never been confirmed as anything at all, because it was never repeated. The silence, in the context of the Arecibo message and the METI debate, is a double-edged thing. On one side, the silence might mean there is nobody out there to receive our signal. If the galaxy is empty, if the great filter is in our past, and we are alone or nearly alone, then the Arecibo message is a stone thrown into an empty ocean. Beautiful, melancholy, harmless. On the other side, the silence might mean exactly what the dark forest theory suggests, that the galaxy is full of civilizations, all of them silent, all of them listening, none of them willing to announce themselves, because they have learned, at some terrible cost, that announcement is dangerous. In this second version, the silence is not the absence of anyone. It is the sound of everyone holding very still, and the Arecibo message rang out into that silence like a bell. There is a different kind of question embedded in the story of the Arecibo message. Not should we have sent it, but if we were going to send it, did we send the right thing? Drake and Sagan designed the message to be maximally universal. They chose mathematics over language, they chose chemistry over culture, they chose binary encoding over any human-specific system. These were wise choices given the constraints, but look at what the message contains. It contains the structure of DNA, the atomic composition of our biochemistry, the approximate number of humans alive, the structure of our solar system, a portrait of a human being. It tells the recipients what we are made of, where we live, and what we look like. If you were designing a message to a civilization of unknown intentions, you might ask yourself, is this the information you want to lead with? Is your biochemical composition, what you are made of, the specific molecules that could potentially be targeted by engineered pathogens, the first thing you want to share? Is your address, the third planet from your sun, the first thing you want to give away? David Brin has raised this point specifically. The Arecibo message, he argues, contains precisely the information that would be most useful to a civilization with hostile intentions: your location, your biology, your technological level, your population size. Frank Drake's response to this critique has consistently been that the message was never intended as a first contact communication with an unknown civilization. It was a demonstration, a proof of concept, a public gesture, a display of technological capability. It was sent to a target 25,000 light-years away specifically because the impracticality of any response in human timescales made the exercise symbolic rather than operational. But the critics point out that intention is not the same as consequence. The Arecibo message was sent. It is traveling. It will arrive. Whatever it achieves, whether nothing or something terrible, it will achieve it without further input from us. We cannot recall it. We cannot modify it. We cannot send a follow-up message explaining that we meant it as a ceremony. In 1974, we spoke, and now we wait, for 50,000 years, to see if anyone answers. The deepest and most enduring concern raised by the Arecibo message is not scientific, it is political, it is ethical, it is about who has the right to make decisions that affect all of humanity. Frank Drake and Carl Sagan did not ask the 7 billion people alive in 1974 whether they wanted to announce their existence to the cosmos. They did not hold a referendum, they did not convene a UN committee, they did not consult with ethicists, or anthropologists, or military strategists, or representatives of every culture on Earth. They pressed a button. This is not to condemn them. The transmission was, in their reasonable estimation, a symbolic gesture with negligible practical consequences. They were probably right about that. And in 1974, the framework for international governance of space activities was in its infancy. The Outer Space Treaty of 1967 had been signed, establishing that space was the province of all humanity, but it said nothing about transmitting messages to potential alien civilizations. But the principle matters, and it matters more urgently now, in a world where METI is becoming increasingly accessible. The Efatoria transmitter in Ukraine, used for Cosmic Call 1 and 2, is a military-grade radar facility. METI International is a small non-profit organization. Any nation with access to a sufficiently powerful radar system could, in principle, transmit a signal toward the stars, and with the development of optical SETI, the use of high-powered lasers as interstellar communication devices, the barriers to METI are falling. In 2015, a group of scientists and scholars issued a declaration calling for a broad international discussion before any further intentional transmissions were made. The declaration explicitly stated that decisions with potential risk to humanity should not be made unilaterally. It called for governance frameworks to be developed, not necessarily to prohibit METI, but to ensure that any future transmissions were the result of a deliberate, informed, internationally sanctioned decision. The declaration was signed by more than 26 prominent researchers. It changed nothing. METI International transmitted anyway. Other transmissions have been made since. The governance framework does not exist. There is no international body with the authority to decide whether humanity transmits or stays silent. There is no process for deciding what we would say if we decided to say something. There is no agreed policy on how to respond if we received something. We are making these decisions by default, by inaction, by the individual choices of individual researchers, by the accumulation of small decisions that together constitute humanity's de facto policy on one of the most consequential questions we have ever faced. Is that good enough? Is it wise enough? Drake and Sagan thought so in 1974. Many researchers today are less sure. Let's follow a hypothetical, not a probable one, just a hypothetical. Suppose that somewhere in Messier 13, 25,000 years from now, a civilization receives the Arecibo message. Suppose they decode it. They recognize the prime factorization of 1679. They arrange the bits in the 23 by 73 grid. They work through the sections and understand each one. They understand that the message came from a planet orbiting a star at roughly this location in the galaxy. They understand that the senders are biological organisms, roughly 176 centimeters tall, bipedal, made of carbon and hydrogen and nitrogen and oxygen and phosphorus. They understand that the senders had a population of approximately 4.3 billion at the time of transmission, and technology sufficient to build a radio dish 305 meters across. What do they do with that information? The optimistic scenario. They compose a reply. They transmit it toward our solar system. It arrives 50,000 years after the Arecibo message was sent. Whatever humanity is by then, if anything calling itself humanity still exists, receives the message. The message contains information about the sending civilization, their mathematics, their biology, their location, their technology. The two civilizations begin a dialogue, conducted at the speed of light, each exchange requiring 50,000 years for a round trip. Over millions of years, a kind of relationship develops. The pessimistic scenario is harder to describe in detail because the specifics depend entirely on the nature of the civilization that receives the message. If the dark forest logic applies, if the receiving civilization considers any newly detected technological species a potential threat, the response might not be a reply. It might be a weapon aimed at the coordinates in the message, launched toward the third planet of the solar system described. Such a weapon would travel at some fraction of the speed of light. It would arrive thousands of years before any warning, because the warning would have to travel from M13 at the speed of light, and any sufficiently capable civilization could send a physical projectile at a meaningful fraction of that speed. We would not know it was coming until it was, possibly, already too late. This is the extreme version of the fear. Most researchers who raise concerns about METI do not consider this scenario likely, but they note that it is possible, and they note that the potential cost, the extinction of intelligent life on Earth, is so high that even a small probability multiplied by that cost produces a large expected risk. Hawking's framework was explicit about this. You should weight the potential downside by both its probability and its magnitude. A small probability of extinction is not nothing. It is, in expected value terms, enormous. There is something that the critics of the Arecibo message sometimes understate, and that the defenders sometimes overstate, and it is worth being clear about. We have been announcing our existence to the universe for more than 100 years, not deliberately, not in any organized or considered way. We have been doing it as a side effect of becoming a technological civilization. The first powerful radio transmissions from Earth date to the early 20th century. Marconi and the development of long-range radio communications, military radar during and after the Second World War, television broadcasting beginning in the late 1930s and expanding through the 1940s and 1950s, commercial radar, cellular communications, GPS. Every one of these technologies leaks signal into space. Some of the signals are aimed upward. Some of them are strong enough to be detectable across meaningful distances with equipment not much more sensitive than our own. The television and radio signals from 1940s and 1950s Earth have now traveled between 70 and 85 light-years from our solar system. Within that sphere, a bubble more than 170 light-years across, any civilization with radio-receiving technology could, in principle, have detected our presence. This fact cuts in two directions. On one hand, it suggests that the Arecibo message was not the decisive announcement of our existence. If there is anyone within 85 light-years with the capability and inclination to detect us, they already know we are here. The Arecibo message didn't change that. On the other hand, there is a meaningful difference between the leakage of commercial radio transmissions and the deliberate, high-powered, precisely aimed transmission of the Arecibo message. The radio and television leakage is extremely weak by the time it travels even a few light-years. It is unlikely to be detectable beyond a handful of light-years without truly extraordinary receiving technology. The Arecibo message, focused by a 305-meter dish, was orders of magnitude more powerful per unit solid angle. It was specifically designed to be detectable across interstellar distances, and it was pointed at a specific target. It was not leaking in all directions, it was a needle sent in a specific direction toward a cluster of 300,000 stars. So the argument that we were already announcing ourselves is partially true and partially misleading. Yes, we have been leaking radio signals for a century. No, those leaking signals are not equivalent in detectability or directionality to the Arecibo message. We announced ourselves quietly and inadvertently, starting in the early 20th century. We announced ourselves loudly and deliberately on November 16, 1974. Both facts are true, neither cancels the other. Let's step back from the specific physics and the specific debates for a moment and sit with the deeper thing. The Arecibo message was not just a radio transmission. It was an act of a very particular kind. It was the first time that human beings, as a species, collectively composed a message intended for minds completely unlike our own, and sent it into the universe with the explicit intention that it be received and understood. Nothing like this had ever been done before, and the act of doing it required making choices that revealed something about what we think we are. We chose to include our chemistry. We think our chemistry is important. We think we are, at some level, our molecules. We chose to include the shape of our DNA. We think the molecule that encodes life is worth communicating. We think any intelligence sophisticated enough to receive our message would find the architecture of terrestrial genetics interesting, or meaningful, or illuminating. We chose to include a picture of a human being. We think our physical form is relevant to who we are. We think our shape, bipedal, bilateral, roughly 176 centimeters tall, says something about us worth saying. We chose to include the address of our solar system. We were not trying to hide. We wanted to be found, or at least we were willing to be found, and we chose to include the instrument that sent the message. We are proud of it. We built this. Here is what we can do. Each of these choices reflects a value judgment, a decision about what matters, about what, from the vast complexity of human civilization in 1974, was essential enough to compress into 1,679 pixels and transmit across 25,000 light-years. What would you have included? What would you leave out? The art? The music? The diversity of languages? The complexity of human emotions? The history of our wars and our discoveries, and our long, slow stumbling toward understanding? There is no way to include all of that in 1,679 binary digits. Drake and Sagan made choices, and the choices they made emphasized science over culture, biology over history, universal language over particular language. This reflects the worldview of mid-20th century science. It reflects the belief, shared by Drake and Sagan and many others, that science and mathematics are the bridge between minds, that the hydrogen atom is the same everywhere, that any being capable of building a radio telescope has independently derived the same periodic table, the same laws of physics, the same mathematical structures. This may be right, it may also be too optimistic. There may be kinds of intelligence, structures of mind, for which our mathematics is not recognizable, not because they lack intelligence, but because intelligence can take forms that do not converge on the specific framework that human neurobiology, human culture, and human scientific history has produced. We don't know. We can't know without contact. But it is worth holding the question. The universe's answer to the Arecibo message, so far, is silence. Not the absolute silence of nothing. The cosmos is full of radio noise, full of pulsars and quasars, and the hiss of the cosmic microwave background, full of signals from natural processes, but no signal that can be identified as the product of intelligence. No structured sequence at a recognizable frequency. No pattern in the noise that says, "We are here. We heard you. We are here." This silence has lasted more than 50 years of active searching. It has lasted through increasing sensitivity, increasing bandwidth, increasing computational power applied to the signal processing. SETI programs today can search more frequencies, at more sensitivity, across more of the sky than Frank Drake could have dreamed of in 1960. And nothing. Carl Sagan called this the Great Silence. He found it troubling, not in a frightening way, but in a philosophically important way. The silence carries information. It tells us something about the universe, about the prevalence of civilizations, about the durability of technological species. The silence might be saying, you are alone, or nearly alone. Life is rarer than you hoped. Intelligence is rarer still. Civilization is vanishingly rare. The universe is mostly physics and chemistry, with consciousness appearing here and there, briefly, like small lights in an enormous dark room. Or the silence might be saying, they are there, but they are not transmitting. Or they are transmitting at frequencies we are not searching. Or they are using communication technologies we have not invented. Or they are too far away for their signals to have reached us yet, even traveling at the speed of light. Or the silence is exactly what the dark forest says it is. We cannot yet distinguish between these possibilities. We do not have enough data. The search is ongoing. What is certain is that the Arecibo message is out there, traveling. It has been traveling since November 16, 1974. It will be traveling until approximately the year 26,974, when it reaches M13, and some fraction of it, attenuated by distance, but still coherent at its core, arrives in the neighborhood of those 300,000 stars. What is there will have changed by then, in ways we cannot predict. The stars themselves will be slightly different. Any civilizations that might exist there will have had 25,000 years of additional development. Whatever they were in 1974, whatever was there, whatever was listening, it will be something different by the time our message arrives. And perhaps, 24,948 years from now, something will be listening when our message arrives. Tonight, the Arecibo Observatory is gone, the platform has fallen, the dish is destroyed. The limestone sinkhole in the mountains of Puerto Rico holds ruins now. The concrete towers, the broken cables, the shattered aluminum panels. Frank Drake is gone. Carl Sagan is gone. The generation of scientists who built the observatory, who designed the message, who pressed the button on November 16, 1974, is mostly gone. Their work remains. The message remains. 1,679 binary digits, arranged in a 23 by 73 grid. 7 sections, numbers, elements, nucleotides, DNA, a human figure, a solar system, a telescope. Every second, the signal travels 300,000 kilometers further from Earth. Every year, it moves approximately 9.46 trillion kilometers across the dark. It is now approximately 51 light-years from home, moving at the speed of light toward a cluster of stars that none of us will live to see it reach. It carries no malice. It carries no fear. It was sent in a spirit of openness, of curiosity, of the particular human drive to reach out across incomprehensible distances and ask, is anyone there? Whether that was wise, whether the openness was courage or recklessness, whether the curiosity was virtue or naivety, is a question that 50 years of debate have not resolved. The scientists who think it was reckless have not been proven right. The scientists who think it was beautiful have not been proven wrong. The universe has not answered in a way that settles the question. The universe is patient. Perhaps there is nobody out there to receive our message. Perhaps the silence is the silence of emptiness, and we are a temporary brightness in a cosmos that has no other minds in it. In that case, the Arecibo message is a monument to the particular strange beauty of being conscious in an unconscious universe. Reaching out, not because anyone can answer, but because reaching out is what consciousness does. Perhaps there is someone out there. Perhaps, 25,000 years from now, something will receive those 1,679 bits, arrange them in a 23 by 73 grid, and understand that once, on a planet orbiting an unremarkable star in the outer spiral arm of a medium-sized galaxy, beings arose that were made of carbon and water and curiosity. Beings who built a dish 305 meters across and pointed it at the sky and said, in the only universal language they could find, here we are. We are small, we are brief, we are made of the same atoms as the stars. We have figured out some of the rules, we are looking for company. Here are our coordinates. Here is our chemistry. Here is what we look like. Here is the machine that sent this message. We pressed a button and we waited. We are still waiting. Sleep well tonight. The message is still traveling. It will be traveling long after all of us are gone, long after everything we have built is dust, long after the sun has exhausted its hydrogen and the inner planets have been swallowed. It will keep going, attenuating as it goes, growing thinner and fainter as it spreads. But at its center, at the exact mathematical center of that radio beam, the information is still intact. The numbers, the molecules, the human figure, the address. Somewhere between here and a cluster of 300,000 stars, traveling at the speed of light since November 16, 1974, is the closest thing our species has ever produced to a message in a bottle. We don't know if anyone will find it. We don't know if finding it would be safe. We don't know if we are alone. But we threw it into the dark. We said, here we are. We exist. We are curious. We are looking for you. And whatever comes next, whether silence, whether wonder, whether something we cannot imagine, we said it. That is what humans do in the dark. They call out,